Today we will be talking about fluorescence, the science behind auroras. Have you ever seen pictures like these and wondered if they were real? Maybe you assumed someone was having some fun on Photoshop, or that they are of other planets, but these are real pictures taken on Earth. How are these lights created, and why do they vary in color? To answer these questions, we will need to start with some underlying concepts of chemistry. First, we will discuss electromagnetic radiation, which is the emission and transmission of electromagnetic waves. We are most familiar with visible light, which is the spectrum of electromagnetic radiation that we can see. These waves can be thought of as energy. Where these waves lie on the spectrum is dependent on their wavelength. Our current understanding of atoms and molecules and their absorption and emission of energy is based on quantum theory. Energy is absorbed and emitted in discrete quantities known as quanta. These quantities are in packets known as photons. This understanding treats light as a particle instead of a wave and can be represented by this equation. Energy equals Planck's constant times velocity. Now we are going to look at the absorption and emission process. Let's illustrate this using energy levels, which are these black lines here. Energy increases as you go up. The electron will start in its ground state here. Now we need a source of energy. Let's use the sun, which provides energy to our system. This energy is absorbed by the electron. Now the electron is in a higher energy state. As energy is released by the electron, it returns to its ground state, and energy is released from the system in the form of light. We now need a mathematical description for this process. We will start with the Rydberg equation for hydrogen, which is given by energy is equal to Planck's constant times the speed of light divided by the wavelength, which is equal to the Rydberg constant times the quantity of 1 over the initial energy level squared minus 1 over the final energy level squared. Next, we will look at an example of calculating the wavelength emitted by hydrogen in a given situation. What is the wavelength of light emitted if an electron moves from the n equals 5 to n equals 2 energy level in a hydrogen atom? First, we will diagram this, drawing out energy levels in the path of our electron. Second, let's write out the Rydberg equation. We know that h, c, and r are all constants that we can plug in known values for. And n naught and n final can be replaced with our two energy levels. When we solve for lambda, we get 434 nanometers. Note that when you actually solve this equation as written, you would get a negative number. However, wavelength cannot be negative. This simply means that we exchanged the values for n and n naught. If you do this, you can just make wavelength positive and assume that wavelength is always positive. Finally, let's look at our wavelength number and see where it would land on the visible light spectrum. 434 nanometers gives us blue light. Now maybe you are wondering why we used a single hydrogen atom for our example. This is because many other atoms and molecules have complexity that make the math for them much more difficult. Electron-electron repulsion is experienced in both atoms and molecules, and vibrational and rotational energy is present in molecules. The result of this in molecules is that while all still absorb energy in the same way, there are a variety of ways that they can emit light. These include, but are not limited to, fluorescence, phosphorescence, incandescence, and so on. This image here depicts the way in which two of these methods of emittance, fluorescence and phosphorescence, occur. They vary in their systems for emitting the energy, though their absorption process is the same. To better understand the behavior of molecules, let's look at the Lewis dot structures of nitrogen and oxygen. Both have additional electron repulsion that can affect their behavior. In each molecule, the two atoms can rotate about each other and also vibrate, pulling closer and further from each other. This demonstrates some of the complexities that we see in molecules that are not just a single hydrogen atom. Now that we have a basic understanding of the emittance of light, we can look at Aurora borealis and Aurora australis. Auroras are comprised of varying colors. These colors are dependent on a variety of factors, including the types of molecules as well as the energy present and the molecular structure of these molecules. Our atmosphere is primarily nitrogen and oxygen. It is these that give us most of the colors. Nitrogen emits violets and blues, while oxygen emits green and red. The layered effect of many auroras is simply a result of which molecules are present at which altitude, and the amount of energy that is put in at a particular altitude. Now we understand what gives auroras its color, but we need a broader scientific context to fully understand this celestial light show. Why are these lights only visible near Earth's poles? Well, this is because solar flares eject massive amounts of photons and electrons. These are then directed by Earth's magnetic field. These photons and electrons thus only bombard the molecules in the most northern and southern parts of the atmosphere. The magnetic field, as well as the path of solar winds, is what creates the unique shapes and motion of auroras. The emission of light from molecules is not only essential to our everyday lives, but it also creates some spectacular phenomena.